Okay, dear students, welcome to my next session on the continuation of this radial probability distribution curves. In the previous session, I have discussed about the wave function versus radius curves as well as square of the wave function versus radius curves. In that, we faced one kind of limitation in the curves. To overcome that one, it indicates that this radial probability distribution curves only gives justification about the probability of finding the electron near nucleus is zero. That will be proved, and the graphical representations are giving that probability of finding electron from certain distance from the nucleus is clearly explained in the form of a graphical representations of radial probability distribution curves. Okay, let us see this one. To understand this radial probability distribution curves, so first of all, we should know what is exactly the radial probability. For that, we have to assume this kind of different concentric shells, which are large number of concentric shells like this, which are said to be assumed around the nucleus with a thickness of distance space between the shells is dr, and whatever the distance volume of the shells is there here, volume of the shell is there, that is nothing but that infinitesimally very small volume, that small volume between the shells is also should be included. Okay, let us see in this one. If you consider this 1, 2, 3, 4, all these concentric shells, and between them we are assuming a very small volume dV, and the distance separation of this space between the shells is dr, in which one orbit 1 radius, if you consider r, the second orbit radius r plus dr we are considering. Between these two orbits, whatever the volume is there, the volume is said to be the volume of the radial shell, means the gap, the space between the shells. That shell is called as radial shell. In that, the volume can be calculated by considering its radius. What is its radius is r plus dr, r plus dr. Now, why to consider this thing is nothing but we should know what is radial probability. So, in this discussion, radial probability you are calculating means the volume between the spaces should be calculated by excluding the volume of this first one, that is the 4/3 pi dr cube. Okay, and in this we are going to consider dr is very small radius, then dr cube and dr square, whatever coming in the expansion of this r plus dr whole cube will be neglected, and we will only consider r square dr. After that, we got, this is the expression called 4 pi r square dr as the volume of the shell with radius r plus dr. So in this discussion, I would like to tell one thing, that radial probability distribution means the probability of finding the electron within a small radial space in the atom. Okay, it depends actually upon the volume of the shell only. So volume of the shell is most important. That volume we have calculated. Simply I can say that radial probability density and whatever the volume we have calculated, the product of this radial probability and the volume of the shell, that is said to be giving radial probability. So what is radial probability? Product of the probability density versus this volume of the shell. As earlier we know that probability density is what? Psi square, and the volume of this shell we got is 4 pi r square dr. Their product we will call it as radial probability. Hope you understand what is the radial probability. There is a lot of chances there to find the electron even in between the concentric shells, the space is provided for the presence of electron. We are going to assume. Okay, let us see that formula. Now you can see this is what we called as, there is a curve obtained by plotting the graph between the size square and volume versus the radius, means distance from the nucleus of the electron, and the curve came like this, in which the radius value is obtained like this curve increasing along x-axis, and the size square value is decreasing here in this direction. So this curve we will call it as radial probability density curve. This curve we will call it as radial probability density curve, and from this nucleus to this distance is the volume of the radial shell, and this is called size square. So size square and volume, their product, now we can call it as radial probability density. That radial probability density formula is came probability density into volume of the radial shell. Probability density we used to call it as size square, and the volume of the radial shell we have already calculated in this before this, that is 4 pi r square dr. Even we can also represent this radial probability as 4 pi r square nl. As we know, r square is nothing but size square. It depends on principal quantum number and azimuthal quantum number. So this graphical representation is giving complete clarity about that electron probability can never be zero, can never become zero near the nucleus. That means nucleus cases comes near nucleus, no electron. Once the electron nucleus distance from the electron is increasing, yes, then only electron can able to find its existence. That means near nucleus no electron should be there. That is proved in the radial probability curve. So now we will check with the different kinds of this size square, means psi wave functions related to particular different orbitals, how that the orbital graphical representations are observed using radial probability distribution curves. Let us see that one. So you are seeing these students, these are called radial probability distribution curves and graphical representations for different kinds of orbitals in this. Over the y-axis we will take 4 pi r square dr, means what we call distribution. Capital D is the symbol we can use in place of this, or if you want, D we have shown. This is for 1s orbital, and the distance here from the nucleus 0.529 in case of hydrogen. So this is the radius. So we have got one peak here. The peak can be calculated by finding n minus L answer. Here n is equals to 1 and L is equals to 0 for 1s orbital. So this is one peak came, and in this there is no nodal plane. So radial nodes you want to calculate means they will give you formula n minus L minus 1, and angular nodes formula is L. If you total these two things, total number of nodes will become n minus 1 only. This is all you will prepare. But the point is, if you see these curves, wherever this curve is meeting this x-axis, that point you will call it as node, where probability will become 0. Maximum probability of finding electron is 0. That means 0 probability is there. That curve will call node. That node we got here 1 for 2s orbital, where n is equals to 2, L is equals to 0 for this 2s orbital. The formula for that one is n minus L minus 1 is the formula. In this n minus L minus 1 we got answer 1. That is why node here 1 we got. So what is the formula is n minus L minus 1, you check it. Okay. Here for 3s orbital there are two peaks came. The peaks formula is n minus L. So here how many peaks came? 2 peaks came for 2s orbital. And coming to this This is what we call the distance. Whatever this point is there, this point is telling the maximum distance from the nucleus, which is the size of this orbital. We are also telling increasing when compared to this 1s. 1s is smaller than 2s. 2s is smaller than 3s. Means size of the orbital is increasing when we are moving away from the nucleus. Means electron. Here n is equal to 3, L is equal to 0. So if you put this N3, L0 here, 3 minus 0 minus 1, we have got 2. That means what is that 2 means? 2 radial nodes we got. We can also call these are radial nodes. Here one more node we have obtained. So how many nodal planes are available for 3s orbital asked means you have to write 2, and whereas how many peaks are obtained means you will write this is n minus L. N minus L for this one is 3, so you got 3 peaks. Coming to 2p orbital, over the y-axis we are observing the distribution means radial probability 4 pi r square dr, whatever we have observed, and here the 2p is also having one peak. If you find n minus L minus 1, here n is equal to 2, L is equal to 1 for this 2p orbital. You put this 2 minus 1 minus 1, 0. That means there is no node observed in the 2p orbital graphical representation, in which n minus L if you find you get 1. That 1 is the number of peaks only. Okay. Next, coming to the 3p orbital, where we have n is equal to 3, L is equal to 1. So n minus L minus 1 if you put here, 3 minus 1 minus 1, you will get 1. That 1 is called one node for this one node. Here how many nodes are there, radial nodes are there for this one asked means 1 comes as the answer. Here in the graph also we have shown. Whereas how many peaks came, 2 peaks came, that is obtained by finding n minus L answer. 3 minus 1 is how much? 2. So how many peaks are obtained in the distribution curve? Here is 2 peaks came for 3p orbital. Coming to 3d orbital, 3d shell, we have 1 peak only came, whereas n is equal to 3, L is equal to 2. That's why 1 peak came, and you put these values in n minus L minus 1 for finding the nodes. 3 minus 2 minus 1. 3 minus 2 minus 1 is how much? 0. That's why there is no nodal plane here, node, in the case of 3D subshell, 3D orbital. So these are the maxima of the peaks. This indicates that much at this point only the maximum finding electron around the nucleus we can see in these orbitals. So these are the graphical representations of the radial probability distribution curves of different orbitals. You can understand. So in the examination, what they will ask means radial node calculation, angular node calculation, and number of peaks calculation they will ask. Radial node calculation formula is n minus L minus 1, and angular nodes is nothing but L. So whatever L is there, that orbital's quantum number value, that is the angular nodes answer. Combination of these two values, if you combine these two, you will get n minus 1. That is called total number of node calculation question in the exam. They will ask from this radial probability distribution curves. I hope you understand this explanation, and you can make use of these videos for further clarity on whatever the concept of Schrodinger wave equations solutions. Have a nice day. Thank you.